Welcome all to another session on our course on line commutated and PWM rectifiers. And today we will talk about the AC-DC converters for EV chargers. So this we are now basically in this part of our lecture in week 11. And at first we will talk about these different types of AC-DC converters for EV chargers. And we will also talk one of the topologies as a dual active bridge. So we'll have a brief overview of different types of onboard and offboard chargers. We'll cover different types, AC, DC, etc. And we will touch upon some of the topologies and some of the analysis and operational issues. And also we will show you many of the commercial development, like the different manufacturers who are making these vehicles, what are their ratings and all, and of course future trend. So today's uh, uh, content is not analytical. So we will not use any mathematical analysis or equations in today's lecture. Primarily, this content is informative. Okay, so basically, we will talk about a wide range of topics, but it is more of information point of view. This is also important because simply only knowing the analytical part is not sufficient. So we need to know what are the different types of chargers for EVs and yeah, and a variety of things like control, communication, etc. So we will talk here, for example, the EV battery voltage levels, power levels for EV chargers. These are important from the specification point of view. Also, different types of connectors, okay, onboard, offboard chargers, and like power electronic topologies. Okay, since this is a course on power electronics, so we will focus on these power electronic topologies for onboard and offboard EV chargers. We'll touch upon also some of the future trends. Okay, and one of the topologies, okay, one of the topologies here, we will cover it in details in the uh, next lecture session, where we will talk about this dual active bridge in details. Okay. Now, so basically, EV chargers are nothing but one form of a PWM rectifier. Okay, because from the AC mains we are charging a DC battery. Okay, so uh, so we have to therefore see that okay, when we charge this uh, uh, through a power electronic converter, which will facilitate the conversion of energy, we have to remember two things. The first thing is that the DC current, the current on the DC side, okay, it has to be well controlled. Okay, because the batteries, they cannot take any arbitrary current. And also, if we want to charge the batteries faster, okay, so we have to inject a well controlled current on the DC side into the battery. And also at the same time, on the AC side, okay, on the AC side, we need to ensure that we are following all the grid standards. And whether we are interfacing with the single phase or with the three phase connections, Single phase is used for low powered, low voltage applications. Three phase is used for higher power and higher voltage applications. So the entire thing, right, is part of the EV chargers. And whatever may be the power handling capacity, the battery management system also, we must remember, the BMS will precisely command the required current, voltage, and power levels to the EV battery. Okay, so one of the important point of this kind of EV charging system is that we must have a galvanic isolation. Okay, this is from the safety point of view, and it is mandatory from uh, compliance with grid standards. Okay, so we can have this isolation, and the low frequency or 50 or 60 hertz, we can have this isolation here, or we can have the high frequency isolation, which will be several kilohertz, okay, in this range. So if we use the low frequency transformer isolation, then we have an input filter, and then we have a rectifier, which must maintain the PFC, power factor correction, and THD, and like that. And then we have a DC link here, and then a DC-DC converter, which fits the uh, voltage, or which produces the voltage which is suitable for the EV battery. On the other hand, if we have the high frequency uh, architecture, then we have this AC grid, we have the input filter, and there is a rectifier with the PFC correction. Okay, and then we have the DC link, and then we have an isolated DC-DC converter, which goes to the battery. Okay, so apart from this galvanic isolation, which is needed for safety point of view, the galvanic isolation also ensures that the leakage current requirements are also minimum. Okay, um, this all these values, okay, how much is the leakage current, how much is the THD, they are all defined by strict standards. Okay, and we have to follow all of these. Now let us talk about the EV battery voltage levels. Okay, in this case we have for the two-wheeler and the three-wheeler EVs. Two-wheeler and three-wheeler EVs are very common in India, and usually the battery voltages are like less than 72 volt. Okay, typically. Now, if I go to four-wheelers, okay, four-wheelers, the maximum number of car manufacturers have a battery voltage of 400 volt usually. In throughout the world, large number of car manufacturers now, as of like 2025, they are making EV, they are working with EV battery voltages of 400 volt. Okay, but there is a trend that to increase the voltage from 400 volt to 800 volt. Okay, and the trend is especially noticeable in case of buses and trucks. As we go into higher voltage, what happens is the for the same power, the current reduces, and therefore the conductor dimension reduces. And so if you go to from 400 to 800 volt, it is expected that the conductor size reduction will be possible. On the other hand, if you keep your conductor size same when you move from 400 to 800 volt, then basically you are increasing your power level. So therefore, then you can actually, for example, a bus or truck, okay, if you, uh, whatever you have designed for a car, right? And now you go to a bus and somehow you can generate a voltage of 800 volt, then you can actually feed in more power, okay? And therefore, the time for charging reduces, okay, as we go into higher and higher power, okay? So there is a distinct trend which we observe, that we are moving towards 800 volt system, okay, so as to like make the charging process faster. And there are also uh, some academic or research uh, articles where we find 1200 or 1600 volt batteries also being proposed. But we can see that within the next 10 years, we will definitely see a lot of 800 volt systems coming into the market. One of the things that we must mention here is that this 800 volt will cause additional insulation stress, and the whole system must be designed for that. Okay. Um, One thing also to note is that suppose we take these 800 volt systems, remember that the voltage of the battery, okay, the voltage of the battery can actually vary substantially, okay. It can vary like from 650 to 920 volt or even more than this. Remember that the 800 volt battery will have a higher voltage when it is fully charged and will have a lower voltage when it is fully discharged. So the charger, EV charger, must be able to charge this battery when the voltage is kind of like not a constant value, it is continuously changing depending on the state of charge of the battery. So generally, all these chargers, we go with a CC mode, okay, constant current mode. CC mode is typically used up to like 90% of the SOC of the battery, after which we move to CV mode. But yeah, this is important because the battery voltage is fluctuating. Okay, as I told you, with 800 volt battery, faster charging times are possible. Um, Remember that one of the points here is that ultimately people would like to uh, have a very fast charging for their cars or like buses or trucks, and want to have an experience which is similar to the petrol stations or the gas stations uh, present days. Like when we go to a petrol station to fill up our petrol in the car, then uh, typically we spend 5 to 10 minutes when this petrol is filled up into the tank of the car. Now, within 10 minutes, we basically fill up the tank to such a value so that we can run for about the next 300, 400 kilometers or even more. So this is something which is a performance measure. And also for EV chargers, this is like an experience which the customer in this case is the driver or the vehicle owner. The vehicle owner would like to have the same experience, and he or she wants to come to the charging station and put the cable into the car so that he or she wants to charge up the battery, and within 10 minutes or 15 minutes, for example, the charger should be able to charge up the battery. Okay, so within 15 minutes, we can say 10 to 15 minutes, the charger should be able to charge up the battery to 80% of SOC. Okay, 80% of the full charge, at least. Okay, so that which will ultimately translate to say 200 kilometers or 300 kilometers. Okay, so uh, this is something uh, which is kind of like a performance measurement of how good a charger is, right? So this is where all manufacturers try to go, like within 10 or 15 minutes, my car can be charged so that it can run to 200, 300 kilometers, even more than this. Okay, many of the modern uh, EV chargers can charge the car with one charging. They can say that they can go to 500 or 600 kilometers. Some research articles are saying that newer kinds of batteries have come and they can, with one charging, they can go to 1000 kilometers or even more. So these are like active areas of research. Uh, but this is a very important performance metric for EV charging. Now, so this was from the voltage point of view, 400 or 800 volt. Now, from the power level of EV chargers, right, we have actually three levels of charging: level 1, level 2, and level 3. Level 1 is less than 3.7 kilowatt. Level 2 is less than 22 kilowatt, and level 3 is less than 400 kilowatt. And level 1 charging typically comes in the residential sector. Okay, so in a uh, uh, residential arrangement, residential power supply, getting 3.667 kilowatt or like more than 3 kilowatt is possible. And so we have this single phase which goes to the customers and 120 or 230 volt. And generally the circuit breakers are like designed to handle such amount of like about 16 amperes. The MCB which we use is like 16 amperes in a residential application. On the other hand, when you go to level 2 charging, okay, we can, we'll go up to like 22 kilowatt. Okay. Now 22 kilowatt cannot be provided by a single phase supply. Okay. By changing the circuit breaker, you can go up to like 7 kilowatt, 7, 8 kilowatt maximum, beyond which you will not be able to operate at single phase. Simply because of the reason that the grid operator will not allow you to take such a high amount of power from a single phase outlet. The reason is that it will unbalance the three phase grid, which the grid operator sees. Okay. The grid operator does not want to unbalance the three phase grid. So if you just draw one phase, a huge amount of power from one phase, then it is going to create a problem. So therefore, up about after certain power, we have to go to three phase systems. Okay, like 400 volt three phase systems, which are very popular in India. In India, we have three phase 400 volt systems. Okay, but they generally give power up to like 22 kilowatt or somewhere like that. And level 3 charging is usually it's DC charging, and the power level can go up to like 400 kilowatt. This is all fast charging. Okay, this is fast charging. Here in the residential case, these are generally overnight charging. Overnight charging means that it will take about 6-7 hours to fully charge the EV battery. Whereas if you go to level 3 charging, then it is very fast charging. So it can charge within 30 minutes, okay, your battery. Of course, it is AC three-phase supply here. Now, one of the things here is that one must remember that we, if we go with this level 3 charging, right, um, uh, it, it is possible from a power converter point of view to have such level 3 charging systems installed at various parts in the city. Okay, it is possible. However, one must remember the what the grid experiences. Okay, you have to remember this very important point is that the grid is not designed to have such large numbers of 400 kilowatt vehicles, okay, uh, in the system. Okay, for example, you may, so if you put a lot of 400 volt, 400 kilowatt charging stations throughout the city, you can think like there are many, many electric vehicles coming to the charging station, and all of them want to charge it very fast. Okay, and they are going into the 400 kilowatt system. It will actually cause a huge stress on the grid, power grid, okay, because it was never designed to work like this way. Okay, so basically, if you start working like a 400 kilowatt, many, many 400 kilowatt chargers, then the grid will experience a huge amount of frequency radiation. Okay, because it was never designed to work like this way. And so we have to think of alternate grid structures. Okay, alternate grid structures or alternate sources of energy. For example, one idea here is that you can have a replaceable batteries, okay, or a temporary storage. So replaceable batteries, what is replaceable battery? Is that you can charge those batteries overnight at a slow fashion so that the grid is not stressed. And when a car comes, take out the old battery and replace it with a fully charged battery in the charging station. So it's like a battery swap. And this also has kind of like picked up a little bit that we do not want to unnecessarily stress the grid because it was never designed to work like this way. Or you can have alternate sources, like you can connect PV sources or local battery energy storage systems. Those are also possible, right? Now, this 400 kilowatt, you see, is projected to grow, okay? Because people would like to have large number of electric vehicles charging simultaneously and within a short span of time. Okay, so it can go to up to megawatt level, okay, for large buses, trucks, etc. So, um, so we have to be careful in in what we are basically um, in which direction we are moving, because we have to also think of the grid, right? And so the fast charging phenomenon, which will require a huge amount of power, is going to cause a lot of problems for the electric grid. And one must remember that. So throughout this lecture, I will show you several links which you can access, and then you can see more information about these details. Okay. Now there are several standards and connectors. Okay. Right. When you uh, talk about electric charging, for example, this is one standard, very common standard, very popular throughout you. It's a combined charging system. Okay, CCS is the combined charging system standard. So it is used in a lot of countries, combined charging system. It's used in a lot of charging, in a lot of countries. Okay, and these connect. So these are some of the connectors that I am showing here. Okay, Shadow is another type of charging protocol or charging this thing, which is typically Japanese manufacturers. They follow the Shadow standard. So when you use this EV charging, the connectors and the charging protocol or the charging standards are different from country to country. Okay, so you can see some standards in USA, some in EU, some in Japan and China, right? And for you also have these IEC standards. These are IEC standards. So one must be kind of like knowing these standards when they want to make a charger and sell it to different markets. Okay, so these are some of the connectors. And here I have shown you a type 2 connector pinout. Okay, here you can see there is one plug for sending pre-insertion signal. So before the charging happens, actually there is a lot of communication that happens between the charger and the electric vehicle. So as to kind of like identify what type of vehicle, what is the battery voltage, and many information is exchanged. So, so if you look into the connector, so there are like uh, some pins for the pre-insertion signals and some pins for the post-insertion signals also. Okay, you can see these ones. And then there is also protective earthing. Okay, so earthing is very important because now we are going to talk about this kind of connectors where people will handle it. Okay, non-technical customers, okay, who are not electrical engineered people, and so they will be handling such a connector. And so protective earthing is very important in this case. Um, so this, and then you have suppose a three-phase connection. Okay, so then you have these three connectors, okay, which are there for the three phases, and then there is a neutral wire. Okay, so this type 2 connectors are usually, you can see Wikipedia and can get a lot of information. This is generally uh, limited to 63 amperes. Okay, now coming to India, okay, there are several standards and connectors which have been established in India, like level 1 AC, level 1 DC, like these. Okay, and for different power levels and different types of vehicles, four-wheeler, three-wheeler, like this. Okay, and we actually have these standards, Bharat AC1, Bharat DC1, these standards. Okay, so the Bharat EV charger AC1 standard follows this type of a connector, 603 IEC 60309. This type you can see here. Okay, and the Bharat EV charger DC1 follows the GBT connector. Okay, so these are some things, and you can see this source to get an idea about these kind of connectors. Okay, for the DC side also, you can see for the DC chargers, we have different standards like SHAdeMO, GBT, CCS. Tesla has its own charging standards. And here you can see that when you use such a standard, okay, these are the different types of connector inlets. Okay, these are the points. It will look like this one. You can just search in the internet or see these references, and you can see what is the voltage level, what is the current level these connectors can handle, and the power level. And what is the communication protocol? You see here, there's a CAN protocol. So as I told you, before and after charging, there is a lot of information that is exchanged between the car and the charging station. And CAN protocol is one communication protocol. And one has to remember that these standards will follow this CAN protocol connection. Okay, many of these standards have already come and has been like for the last 10 to 15 years. Okay, uh, but in future, we are looking at megawatt level charging systems, like which will be able to handle very large amounts of current, 3000 ampere and 1500 voltage level. So these are like upcoming connectors. So we will have different types of connectors. Okay. One thing that one must remember, that if we go for this kind of high voltage, high current rating, the safety of the personnel, the safety of the driver, uh, this must be absolutely, uh, I mean, it is very stringent requirements. Okay, because we are talking about like 1500 volt, and an electrocution in with 1500 volt can be fatal. And this 3000 amperes of current, which means if there is any short circuit, okay, on these connectors, the amount of current that will go through is enormous. Okay, and it can, I mean, so one must be very careful when we want to work with such high voltage levels and currents. Okay. Now, when we classify the EV chargers, so there are onboard chargers, like dedicated onboard chargers, integrated OBCs, and inductive wireless charging and offboard DC charging. We are just going to briefly look at these. What is dedicated onboard charger? Onboard dedicated charger means, so you have the grid here, and then this grid goes inside the electric vehicle. Inside the electric vehicle, it is converted from this AC to DC here. And then you have a isolated DC-DC converter. Okay, this is the isolated DC-DC converter, right? So this side is DC and this side is DC, but it is high frequency. There is a high frequency transformer in between. Okay. And then we have the battery here. So typically these onboard chargers can be used in commercial or domestic outlet, but typically they are used like overnight charging. Okay. Um, yeah. Now, in some cases, we have what is known as the integrated onboard charger. What is the integrated onboard charger? The integrated charger is something like you have the single phase, it's a grid, okay, and then inside the EV, okay, so there is this battery here, and then there is an AC to DC converter here, and then there is a DC-DC converter, okay, is a DC-DC converter here. But in this case, what happens is the motor's stator winding is used as the filter come isolation. Okay, it can be used. Okay, sometimes this is also not used, but the motor's filter. So this concept is very interesting. It is like this way. The motor has 3 stator windings, okay, like this. Okay, and suppose you have connected the grid here, right? Now, uh, so you can have a switch. So let me just redraw this one. So this is, for example, let me draw it clearly. So suppose this is the motor winding, okay, the stator winding. I'm not drawing the rotor. So this is the stator winding of the motor. And uh, during the normal operation, so there are two switches here. Okay, suppose I give this name as S1, this as S2, and here is the grid, three-phase grid. Okay. Now, this is the motor stator winding. And of course, then you have a AC to DC converter bidirectional. And then you have this like this way, what we have shown here, then the DC-DC converter and a battery here. So under normal condition, what happens is that when you are driving the electric vehicle, you will open S1 and close S2. Okay. So then this winding, the stator winding of the motor is basically like a motor. Okay. It will act as a motor and the energy will flow seamlessly from the battery to the motor for motoring operation and from the motor into the battery for during regeneration operation. Now, when you want to charge, okay, the same winding, okay, so when you want to charge it, so what you do then is you will then open this winding and close this winding here. Okay, close it. So what happens then is that then the same winding, the stator winding, will now act as an isolator and the filter for the uh, for the battery charging. Okay, of course, one important point here is that you have to lock the motor. Okay, we have to make certain mechanism. Otherwise, the motor, if you just allow a balanced current to flow, it will start to rotate. Okay, so you have to make some arrangement so that so it's like a short circuit. Otherwise, then so you have to make some arrangement so that this is taken care of, right? And you can use the same motors winding. So this is this on integrated charger. So they can use this one, okay, as the same charging. So there are certain interesting papers on this. Okay, you can have a look into it. The other way by which we can charge is, of course, this is very important, is the wireless charging. There is a lot of work which is going on. Okay, and so here there is uh, a wireless transformer. There is a transformer, and there is a magnetic coupling between an off-board high frequency inverter and on-board. So this is off-board. Okay, this is maybe outside. Okay, it may be part of the. It may be also embedded inside the road. Okay, and there is a high frequency. Uh, yeah, it can be inductively coupled or it can be also capacitively coupled. So wireless charging is a very important way of charging the battery, and a lot of work is going on. Wireless charging has been there for like mobile charging for a long time now, and there are applications where electric vehicles are getting charged through this one. So, but again, still, uh, wireless charging has one drawback, and that is that the amount of power that can be transferred through a conductor is more than what can be transferred wirelessly. And so, because most of the car manufacturers are now concentrating on reducing the time for charging, okay, so they wanted to charge it very fast. In that respect, conductor-based charging is better than a wireless charging. Okay, so you can, but wireless charging gives you many flexibilities. Okay, so you don't have to have a single point of charging, even a strip of road, okay, long road, if you can embed these high frequency transformers inside the road, okay, you can actually charge the whole car while the car is traveling. Okay, so embedded chargers under the road. So that is also possible. Maybe it is a bit expensive, but such a possibility exists. Okay. Now, off-board DC charging, when you say the off-board DC charging, then most of the power conversion takes place outside the vehicle. So basically, this off-board, so this part is entirely now outside the electric vehicle, right? And then we have an AC to DC converter first, and then a DC-DC converter, okay, and which goes into the battery. So dedicated onboard uh, chargers and offboard DC chargers are now widely used. Okay, so at some point of time, we say that DC charging is faster than AC charging. Okay, so basically we go into DC chargers, right? So DC charging is uh, gives us higher amount of power. Most of the commercial manufacturers which are going like more than 300 or 400 kilowatt, they are opting for DC charging. Okay, so let us see some of the converter topologies, okay, used in onboard charging. OBC means onboard charging. So here you can see um, some of the topologies I will talk about. So in general, what you will see there is always a input grid tied PFC converter, which improves the power factor. And in the second stage, there is a galvanically isolated DC-DC stage. Okay. And so, of course, active, so there are also like other techniques like active power decoupling. We will not talk about it, but this term you can look it up. Okay. For single phase OBCs, okay, active power decoupling technique, you can have a look into the internet and see that there is a 2 omega power oscillation with a single phase, and active power decoupling is a important technique to reduce it. Okay, to reduce the size of the intermediate DC link capacitor. Okay, can have a look into it. But anyway, some of the important, so we want to say is that there is a first stage, which is a grid tied PFC converter, and a second stage, generally an isolated DC-DC stage. Okay, so what are the different topologies which we used? For the front end AC to DC side, we have the boost PFC rectifier or bridgeless totem pole PFC. And uh, for the three-phase onboard chargers, we have the conventional two-level VSC and VNR rectifier and T-type rectifier. These are very important, and all of these we have actually covered in the course. Okay, the boost PFC, the bridgeless totem pole PFC or VSC, VNR rectifier, T-type, these we have already covered. Okay, and we have seen the benefits and drawbacks of all these types of converters and also their control in the previous week of the lecture session, right? Uh, on the other hand, there are also in the onboard chargers, we have isolated DC-DC converter. And one of the important requirement is to have soft switching characteristics over wide range because we want to increase the efficiency of the converter, right? And the commonly used isolated DC-DC converters like phase shift full bridge, LLC resonant converter, DAB, and CLLC. These are shown here. We have not covered these converters because in this course, our focus has been on the rectifier application. We have not talked about DC-DC converters. Although in a subsequent lecture, I will uh, briefly talk about the DAB, okay, the dual active bridge converter, because this is something which we feel is a very important DC-DC converter. And unless this is taught, okay, unless this is understood, the whole picture from AC to DC side is not complete. So we'll talk about this dual active bridge. Basically, the all these PSFB, LLC or CLLC, you can understand that there are two bridges. Okay, basically there's a H bridge or full bridge on the input side of the DC. Generally, this is a higher voltage, and this is the generally the high voltage, and this is the low voltage. Okay, so basically you have this H bridge here, and you can produce a square wave or a quasi square wave and it at the input. And if you have by unidirectional power flow, you will use diodes. If you want a bidirectional power flow, you will use MOSFETs, okay, to transfer the power. And so at this side, you also can have a quasi square wave, right? And so across this inductor, you will have on the left hand, right hand side, you will have two voltage sources, right? And then you can allow the power to flow seamlessly from left to right or right to left. You can also have LLC, so you can make an LC converter here also. Then apart from the voltage, okay, the voltage may be a square wave or a quasi square wave, but the current can be made sinusoidal. Okay, the benefit of having a sinusoidal current is you can turn on and turn off the switch at the zero crossings of the current. So apart from zero voltage switching, we can also have zero current switching in these converters. Okay, so these things we have briefly going to touch upon in the DAB when we talk about it. But these are some of the important isolated DC-DC converter used in onboard chargers. And now we will show you some commercial examples. Okay, we have taken these uh, material from this reference here. You can look into these references. Okay, so for example, this is taken from General Motors Chevrolet. Okay, and here you can see they have used a PFC converter. Okay, this is the boost PFC, but here they have used an interleaving. You can see this is one boost PFC. So this is one boost PFC, and then there is another boost PFC like this one. Okay, and then they are paralleled at this point, right? So what happens is by paralleling at the input, what we have done is these two currents, okay, they sum up. Okay, so the current comes here and gets divided into two parts, two parallel parts. And what happens is it effectively doubles the current ripple frequency and reduces the size of the components. Okay, so these two inductor currents will have a phase shift between them, and therefore this current here will have less amount of ripple frequency. Okay, and this is one thing that is used in an interleaved PFC converter. And on the right hand side, you can see here there is a DC to DC converter, okay, and which ultimately feeds to the battery, right? So these are some of the specifications. You can see here that it's an universal input, and input current is 16 ampere max, and output current is 13 ampere. And the efficiency here is 93% to 95%. Okay, and this much of power. And these are very important terms: power density and volume power density. I mean, kilowatt per kilogram and kilowatt per liter. Okay, these are very important specifications apart from the power and voltage. How well you have designed your charger. Okay. Another example is like a Tesla Model 3. Here they have used a different circuit topology. Okay. And there is a three-phase active rectifier. Okay. What they have done is that for this 11.5 kilowatt, they have used three sets. You can see here, set 1, there is set 2, and there is set 3. Okay. Three parallel sets of such rectifiers. In each set, what do they have? They have a front end conventional three-phase rectifier, then a DC link, and then LLC resonant full bridge. Okay, so LLC resonant, this is the full bridge resonant, and then they have the diode rectifier which forms the battery. Okay, many of these converters also use a capacitor here. Okay, and primarily it is done so that the ripple frequency flows through the capacitor and the DC flows through the battery. Although this thing that this has come from the fact that uh, it was it is assumed that the batteries are, if you allow the ripple current to flow through the batteries, then the battery will heat up very quickly. However, newer generation batteries are coming up with different technologies, and in many cases, now we can actually remove. So the studies have shown that this capacitor at the output may be removed, and the battery can actually take up the ripple current coming out of the converter. Okay, so this is some advantage, and of course, it will make the converter further compact. You can see some latest developments in this regard through some papers. Okay, and then we have also the off-board DC chargers. Off-board DC chargers means they will give, uh, so at the terminal, you have the DC available. Okay, it's no longer made inside the car. And so they can operate with an ultra wide output voltage range, 200 to 1000 volts, and they are having generally a modular design. Okay. Yeah, so therefore you can see some of these. For example, this is the Enercon charger, e-charger 600. It is, you can see this is very high power rating. It's an off-board charger. Off-board means actually this part, that the AC part, that comes in a container. Okay, in Enercon, you can see the Enercons, you can search in internet, this e-charger 600. So it comes, there's a container which gives this one. And then there is this uh, charging unit, okay, which is installed on ground. And the output of the charging unit, this is where the cables go, okay. And the user can take these cables and put it inside the car, okay. So there are 4 charging points available here, and the maximum power per charging point is very high. I mean, 350 kilowatt means you can charge the car in like within 1 hour, definitely. And the 200 to 950, but the efficiency, you see 94%. And we have seen newer generation of chargers which have higher efficiency than this. Okay. Um, you can also have, see here also there is an isolation. You can see this is the isolation. Isolation is mandatory for all such chargers, okay, from safety point of view. But the isolation can also be done like in ABB Tera HP, it can be done at the low frequency, okay. Yeah, so galvanic isolation is provided by low frequency transformer. So you have this grid and this isolation transformer and then filter and yeah, 3-channel interleaved buck converter. Okay, so there's a different one. So you can see here, this is like a buck converter, okay, interleaved. Interleaved means at the output, they have been paralleled. Okay, here you can see this is paralleled here. Okay, so it's to increase the current rating. And then we have the EV battery pack. Right? Okay. And this table, which we have taken from this IEEE Access uh, document, this is a nice uh, review paper. And here you can see the different manufacturers. Okay, there are a lot of manufacturers now which are commercially producing fast chargers. And you can see, like, for example, you can see the voltage range, what type of output voltage, and all of them are almost like 400-volt three-phase AC. And the power range is like, we are talking like 300 kilowatt. Many of them are 300 kilowatt or more. Okay. So the newer generations, like we are touching like 400 kilowatt. Okay. You can see here. And all of them, you can see the charging standard, they are CCS and SHAdeMO standard. These two are very common. Okay. So CCS has also changed to CCS2 and like that. And like you can see the current levels and all. Okay, one of the important point here about the chargers is the mass and the volume of the charger. Okay, and here you can see some of the values where we will see how much is the power density. So these red and green and blue have been marked by the authors here. Okay, and they have indicated, so they have made a matrix that, okay, if the yellow ones are average quantities, the red ones are low quantities, and the green ones are high quantities. So in this case of the power density, we can see that this one has a very high power density, 0.37 like that, or even this one has 0.52. Uh, Also, we have to see the peak efficiency, and usually 95% is something which is quite acceptable and like a de facto uh, value, which most of the manufacturers will stick to, that at least the efficiency should be 95% end to end. Okay. But many of the chargers, they are like, you can see, they are even crossing 97%. Okay. And that is also very important. Okay. How much we are going to get. Okay. And also how to dissipate the heat, right? Because if 400 kilowatt is flowing with an efficiency of 97%, then 3% is lost. Okay, so 3% of 400 is something like 12 kilowatt. And so 12 kilowatt of power must be dissipated by the charger. And that is not an easy task to do. Uh, so the temperature will go up like that. So it's this is where the efficiency is important. Okay. And apart from this, we also should have isolation monitoring, because as I told you, um, AC and DC, so the safety of the personnel is very important. So DC chargers are mobile unearth IT systems. Okay. And AC chargers are typically earth systems. So this is a difference between these AC and DC chargers. But before the actual charging process can begin, okay, the vehicle and chargers actually communicate, okay, and say that, okay, there is no isolation fault and the charging can safely begin. Okay. So there are these standards which one must keep in mind, uh, which will, the charger will normally detect the isolation levels, okay, before you can begin the charging process. This is important. Another important is the communication protocol also. So before and at the end of the charging, the charger and the vehicle should communicate between each other. And a common protocol is this protocol, OCPP, okay, Open Charge Point Protocol. So it is used for a variety of reasons, like identifying the type of vehicle, if you want to do the transaction handling, also security. Okay. So security of the card when it is charging, and communication with grid operator. So all these things are taken care of by the communication system. And for that, a common protocol, which is kind of like accepted by all different manufacturers, is the OCPP communication protocol. Now, future trends, of course, if I look into the future trend, we are going to increase the power and the voltage levels of EV chargers. It's going on, and we will see more and more voltage, higher voltages and more power. But at the same time, we must look into high efficiency and high power density converter. And this has been the driving force. So silicon carbide and gallium nitride, these two devices, in fact, have revolutionized the high power density converters. And um silicon carbide is basically the popularity of silicon carbide is largely driven by different EV manufacturers. Okay, so this WBG, wide bandgap semiconductor devices, are going to play a very important role in the development of high power chargers. Of course, you will have switching, soft switching like ZVS and ZCS to reduce the switching loss, high switching frequency to reduce the size of the converter. Okay, so typically we will not go less than 20 or 30 kilohertz for these kind of chargers. And planar magnetics. So basically, instead of uh, um, yeah, integrated magnetic designing, so planar magnetics with PCB winding. Okay, so the in planar, some of the configurations of this planar magnetics, we actually make, we do not use the wire. We use the magnetic, the wire, the routing of the PCB. Okay, the way we route it, uh, the PCB itself becomes the different sets of wires across the magnetic material. Okay, and uh, you can see a lot of papers coming up, but there are other types of wires also. We use leads wire. We do not use the normal um, traditional wires. We use leads wires because the skin depth is small in this leads wire. And so that is also one way of doing things. But PCB, uh, planar magnetics with PCB winding, actually, we have experimented that also in our labs, and they come out to be very nice, actually. Okay. Um, and of course, improvements have to be made not only in peak efficiency, but also in the efficiency of the entire charge. So basically, we also think of like uh, when the charging starts and when the charging ends, at throughout this whole time, okay, the efficiency of the entire charging cycle must be increased. And of course, fault tolerant topologies, health monitoring. Okay, health monitoring is very important from the battery point of view so as to give the optimum charging performance. And of course, another one is a future trend is bidirectional OBCs. So V2X, okay, grid to vehicle, vehicle to grid, or vehicle to home, these kind of applications are being thought of. And each with these two-stage onboard chargers, each efficiency, each stage is going to 99% nowadays, the target. And overall efficiency, many are considering this as a benchmark, 98%. Okay. And we can think like this way. Okay. And also at the medium voltage, people are thinking about SSTs, solid state transformers. We'll talk about it a little bit in the next week. Okay, solid state transformer based megawatt charging system. So these are particularly good when there is a large amount of many vehicles being charged from the medium voltage directly. Okay, there this kind of things are advantageous. Okay, so you can see some of the references that we have used in this paper. So in summary, I should say that this lecture was more like an information session. That's how we have designed it, so as to like get a good overview of different types of charging technologies, of course, from the power electronic point of view, not from other sides. But this was an informative session. We did not go into the mathematical analysis or detailed step-by-step analysis of waveforms and all. We have not used those things. One of the topologies that we have indicated here, the dual active bridge, we will take it up in the next session and we will go through it in details with an with a mathematical analysis. And we feel that it is one of the most important converters for this onboard charging or for other purposes as well, because it has this bidirectional capacity. And if you understand DAB, you can actually derive the other converters like PSFB and all. So it is good to understand that DAB operation, which we'll take up in the next session. Thank you.